In this video, I'm going to spend some time going over what exactly needs to be done on this project. Let's begin by looking at the files that are in the Google Docs directory. These are it, and they consist of the SVM predict and train, the data that can be read from the SVM toy, which mimics the SVM toy that comes with the package, the data from Project 4, which you can see is a little bit larger than the data that we played with, and two codes. One is SVM toy and SVM toy probability. One we're going to focus on for the project is the one that has the probability associated with it. This one's just placed there for a little bit of fun. If you look at it, it will essentially open the data file, the one that we can save using the SVM toy, and run the code on it. Let's run it and you'll see what I mean. So here's the result. If you want to change this data set, you can go in, run SVM toy that came with SVM package, and just go in and set a series of points. And let's see, let's just set a series of points just for kicks. You can see, let's see, you can only set 3 regions of points. There, once you do this, you're going back to blue. You could run it, and we can save it. And if we ran in here and just saved it on top of data, you see what we get here. Come back and run SVM toy again, and you'll see the same set of data shows up. Over here you'll see the colors are slightly different, but you see the same pattern. If you want to see the same exact results, you have to match this area to our code. So let's see. T2C100. Let's go down or go up into here. T2C100. Get rid of that for right now. Let's run it again, and you see the same pattern. Now what you're looking at is you're also seeing that you're seeing a flip in the coordinate. When you place your cursor up here, it's 0, 0. This is X and Y goes down. Over here, this goes, the Y goes up and the X goes in the same direction. So you're seeing a flip of the image. This is flipped over, mirrored up and down. It's like looking at it in lake water, where the water comes across here, and basically that's what you're looking at. So this SVM toy is just to get you used to playing with the toy and then running it in MATLAB, reading the file in MATLAB to see what it does. Since we decided to stick to that format, and that format is read from here to here, we will do the same thing with the other file. Now, the other file is already set up, and it looks very much similar, except first of all it reads project. It goes all the way down. What we're going to do is we're going to put some breakpoints and look and see what each section of the code does. This section simply reads the file. That's all it's doing. So we're reading the file through here. Right in here, we're basically going to print our features on the feature space. We have chosen, just like with SVM toy, there's 2 features. One's X, the other one Y. There could be multiple features, but when you get past 2 dimensions, it's hard to visualize, which is why we're sticking in 2 dimensions for a while. So we basically take a look at this, and We're going to breakpoint it about right here, run this code, and we see, unfortunately, we see 4 features. We see a red, a blue, a green, and then a light blue. If I load Project 3 in here, what you're seeing is it coalesces the dark blue and the light blue features into one feature here. So you see another feature. This is the green. This, of course, is flipped over, so this is the red, which is the light blue here. So there's no way to match this versus that, but at least you can load that data file in and take a look at it and see what you think. From this point, we want to classify. Here's where your variable space. You see in the code I've written 3 individual lines here, commented first 2, so that tells you right quick this is an area where you can play with. The B, if you look at the help file for SVM, is that I wish for SVM train to produce a probability estimate here. These are 2 parameters, the C and the G. I'll let you read those, but you go on here, and what you're going to find is you're going to also find me producing a mesh grid. Now this mesh grid is here in order to produce a plot. It's not to put a background grid on it, and I'll talk about that as part of the project assignment in a little bit. So I come in here and I produce a series of points in the feature space right here, where I create feature space, then I reshape them, and we're going to step through this and take a look at each individual line and see what each line is doing. First, let's train it. So we're going to step. What you're going to see down here is, in a minute, you're going to see it get finished training. Okay, I've trained. It took 11 seconds. I'm sitting right here. Now, if I do a step again, you'll look at f of x is a 201 by 201, 201 by 201. Now, one of the things we see is the features that we've sent to it is an 8,000 by 2. The target's 8,000 by 1. So if we're going to send another set of features to it, it needs to be some n by 2. It needs to have the same number of features. So I need a feature x and a feature y. Now these are listed as a 8,000 by 2, not 2 features that are f of x, which are in the x, and f of y, which is in the y. A 200 by 200 or 201 by 201 is not the right dimension, so we reshape it. Step 1, and what you'll see is you'll see a 40,000 by 1. That's the x features. Step again, you'll see all the y features, but these go together to create the feet. Okay, you notice that it's highlighting the FEAT and the FEAT here. Do one step, and what you'll notice is it's a 40,000 by 2. Okay, there are 40,000 features, 40,000 points in this domain, x and y, that are going to be sent to the predict. I could care less what the targets are, so I'm going to make them all a target with 3 times 1. Step, what it's done is it's just created the same. What you notice is 8,000 by 1, 8,000 by 2, 40,000 by 1, 40,000 by 2. Do one step. It may take a few seconds. It will produce. Now this accuracy is unimportant really, because I've sent fake targets at it. All the targets, if you notice, they're all 3s. So this is telling you how many 3s there are actually in the domain. Next thing is I've created a set of targets that are going to come back to me, a Q and a probability estimate. First thing I'm going to do is I'm going to reshape. Well, I'm going to hit the hold on, but that didn't need to be right there. I'm going to reshape my, so you have to think of this CZ as being the elevation of a plot. So I'm going to reshape this FX and FY back to, and I probably didn't even need to do this, but you notice it's a 2001 by 2001. Oh, I'm sorry, I do need to do this. I'm reshaping the Z. So this is the elevation. I've already got the FX and FY. Do a step, and what I'm doing is number of targets is 4, and I'm doing a contour in a second. Now it threw it on this plot. So what you see is a contour, and then for here, let me sort of pull this out so we can see as much as possible. What you're seeing here is the contour. This is the number of contour zones, so to speak. Here, we'll do a step, color bar. The color bar got added to the right. And we'll do one more step. I don't really think, I don't need to deal with this as part of the explanation here. What has happened here is feature 4 is the dark red. So here's your dark red. There's some of your dark red. There's some of your dark red. Pretty obviously that that's blue. However, the part that always concerns me about this is that it has identified this entire region right here as being feature 4, when actually only 1, 2, 3, 4, 5, 6, 7, 8 points are in here to satisfy or to support that. It also is telling me all this is feature 4 as well, when actually there's no data over here to support the existence of this being classified as feature 4. This is the part of SVM that I don't like, and there's a way around this to use SVM to help you decide this. Here is the green here, this blue is SVM classifying all this light blue area as feature 2, I'm guessing. So what you're seeing is some weaknesses in this, and we have a way of strengthening this up, and that's the whole point of this project. So, and of course the dark blue, it shows this orange area is the classified as the dark blue. Even, and in there's a little bit of area over here classified as dark blue, even though there's only 1 point existing in that orange area. So let's continue with this. Okay, as we step through here, I think all I'm doing here is putting the data back over each other. So you see me putting the data back over the plot. So if you watch this plot as I step through here, you see it plotting, and then you put one more and it puts the legend on here. So here's your legend. Target 1 is the red, target 2 is the green. The reason I'm doing that, putting that on there is, for example, look at target 2 is green. We look over here, you see 2. This means that the contours are such that the 2, this blue, should be classified. The green and the blue go together. For example, this is target 4. Target 4 is this dark red. So all this dark red goes, this dark red here goes with the blue right here. Okay, so this should step. Okay, now we're going to plot the probabilities. We do the same thing. I'm indexing through the number of targets, which should be 4. I'm producing a figure for each one of them, holding on. I'm reshaping the probability. Now let's review the probability. Flew back from the predict right here, or flew back. It basically came out of the SVM predict. So put in my features, it gave me the probability that at any particular point it existed. What's the probability that it was whatever feature? I have, if you look at probability, there's 4 of them. It's 40,000 by 4. That's 4 because there are 4 targets. If you step through here, hold it, let's move the figure over here, and sort of shrink this down a little bit. As we step through it, okay, we're going to reshape. We're reshaping. This CON is contour, but it's a contour of the probabilities. Probabilities should go between 0 and 1. We hit a contour, and here's what we see. Now, put the color bar on it, but we need to step through and put our points back on it. So here's our points. So we're laying our points back on top of it, and then we throw a target on there. So there's target 1. You see there it is a slight probability over in here of this being target 1, even though there's no points that exist over there. But most of the probabilities that are high are very well contained to the where the red exists. Now, one of the things you notice, and here let's take a look at this. If we take off all these points and look at the contour, you notice there's a valley, if you will, between here and here. This is a high spot of 0.9 roughly, maybe up to 1, a low spot of maybe 0.2, 0.1, and then a high spot here. So there's a valley right here. And if you notice, the red is existing throughout there. The reason that valley exists is because, notice, the blue occupied sort of part of that space. So too did the dark blue. So the existence of this light blue and the dark blue shoved that probability down, because there will be an area where right in here is a mix between all 3 of these targets. So let me bring that back. Shrink that back down. So what we'll do now is we'll step through here, and we'll notice it will produce the plot for target 2 the same exact way. Now it's going to put the data. And put the title. So here's target 2. You notice here's, obviously the green dots are target 2, and you notice there's the probability regime. You notice it's very high probability here, even though there exist only 2 points. A very strange probability. So it's like 55% roughly chance that it's target 2 right over in here. Okay, so what I'm getting at is the area right here has no points to support it. This area right here has very few points to support it. So as we go through this, we need to be aware of some of that. And what I'm going to do is put a breakpoint here and jump through the other 2. What you're going to see is here's target 4, and we'll look at target 3, which is particularly annoying to me. And here's the reason it's annoying, is because if you look at this area right here, it's saying there's a 70 to 80% chance that this is target 3, when in fact in this region right there, there's no points of any kind to support that. That's very annoying. And one of the weaknesses that I think of the method. However, we can use the method itself to fix that. And that's, again, what my point is. The next section, and I'm going to go ahead and knock these plots off. And go through surface plots. And we'll do these one at a time. Step through, it produces a figure. Here's the figure. We're reshaping, put the contours on there, so we reshaped, take the probabilities and put back on there just like below, above. We just produced a surface there. And here I'm just producing a lit surface. So you see, you know, there's like the cameras to the right. You'll see a lit surface on the right side of a hill. So if this is a hill right here, you'll see the light shining on here. You can see all the ripples this way. I think that's pretty neat, but in any case, now we throw, hang on, we're throwing our points on it. You don't see them because they're under the surface. This one's not, though. And as we go through here, I'll just put a breakpoint here. Well, I'll keep stepping. You'll see the points getting thrown on. You'll see some of the blue. The reason this is interesting is because any elevation of this surface will block out because these points are laid upon the 0 plane. So right in here, you'll see there's a 0 probability that we're target 1. And as you go through, you'll see the color bar in target 1. I'm going to go ahead and do continue. Look at target 2. There's target 2. Do a continue. Look at target 3, which this one I'm going to pause and take a look at. This is the one that particularly bothersome to me because this area right here is a hill. That is a hill. So if you start concerning yourself a little bit, you'll see that there's no evidence to support that hill at all. There's nothing. That hill should not be here. For that matter, there's a little ridge right here. And a little bump over here. That's sort of in question, but there are a few points that might go under that hill. I don't know. But let's take a look at the surface in this way. We'll come over, take a look, and rotate the surface up. And you'll see the points up under the surface. So here's the points up under the surface. And you'll see the big hill, the spike, if you will, that exists right here. So there's your spike that really shouldn't be there. So our goal is to get rid of that. And for that matter, this region over here, this little hill, this little ridge that comes around here shouldn't be there as well, because there's no data to support it. So once you do this, let's see, step it one more time. I guess we have one more. Yeah, target 4. There's your target 4. It also has a little ridge right here. And I think we do a step and we're done with the code. Now the key is I want to have some capability of removing those ridges. And probably, I'm going to go ahead and stop that. Probably the easiest thing to do is run the code again, and let's take a look at our data structure. I'll run it down to here, and I'm just going to bring it in to approximately right here. Okay, so you run the code, you have your features. What you have is 8,000 points with 2 features on them. Let's go through and look at what these look like. This is the X, if you will, and Y coordinates of a particular feature. X and when I say that, of a particular data point. These are classified as feature 1 and there's feature 2. Now your targets are lined up in the same way. There's 8,000 by one of those, 8,000 by 2. So for this particular point in the feature space, the target is 1. And as you go through, what you find out is just the way the data was constructed. All feature 1 takes place first, then feature 2, then feature 3, and then finally feature 4. So what I'm thinking is I'm going to create a feature 5. So let's do it right here. Feature 5 is going to be a background grid. So say background grid, and since I do not know the number of features this code could read in our particular case, it turns out to be 4. I'll say features are, and then I'll just say maximum of the target. Actually, I really should rename this to targets are maximum of the targets. Now here's the nice thing about this is I can select this and right click it and evaluate the selection. Okay, the targets are 4. So what I could actually do is just say something maybe like new target. New target is equal to not 4 but 5. I want a 5th target here. Then my background grid. Well, one of the things I could do is just look down here and say, yeah, looks okay. So I can just grab these lines. I'm going to adjust them though. Come back up here and reuse them, but that's a little bit much. So I think what I might start with is just 0.1 here, and for that matter I might just want to call that dxy is equal to 0.1, so I can just change this instead of changing the other. Dxy, and then hit dxy, and then I'm reshaping it, and then I get my features out of this. So if I do this, I will have let's go ahead and hit that. Well, let's do this. Let's hit this. Let's evaluate the selection. What I've got now is a feat, which is a set of features that are listed in the XY, and you can see the pattern here. There's 121 of them. What I really want to do now is I want to append that feat to the end of the features. So how do I do that? One of the ways you could do it is just do feat. Is it plural? Yes, it's plural. It's equal to cat for concatenate, and it tells you the dimension. I want to concatenate, see at the bottom or the top, features, and then feats, and then I want to targets equals to cat. Got to have the same thing here in the targets. Is it targets plural? Yes, targets. And then okay, now I've got to come up with new target time ones, and I need it to be the number of rows, so I need it to be the size of feet the first dimension, then by 1. I think I'm okay. I see a few issues here, and that's that. We're going to attempt to step our way through this. Here we go. Let's evaluate that selection. Did my features increase in size? 8,121. Targets still 8,000. Hopefully. Evaluate the selection. And now the targets 8,121. Now let's look at the features and the targets, and what you'll see is you'll see the appearance at 8,000 of the 5th. So let's run down to 8,000 and see if we see our pattern. And sure enough, what you see is at 8,000 you see our pattern that we concatenated to the bottom of that. Okay, so I feel pretty comfortable that this is a good, I've added this as a feature. I'm going to hit a save, and I'm going to rerun this. Now this is not saved on the Google Drive, so you have to do this. So let's put a breakpoint right here. I'm going to run it. I'm going to continue, and then I'm going to continue again and look at the plot. Now what you see is a pretty sparse background grid. That doesn't look very sparse compared to the data here. So I might want to tighten that up a little bit. So let's say I put a 0, 1, tighten it up a lot. And I'll just go ahead and take those 2 breakpoints out. It'll stop right here. I'll hit a save, run it again. Now that's a little extreme there. That's too tight. So I might run back about 0.5. I'll save that, run it again. Yeah, that might go by fine, or maybe I want to do it at 0.25. And that's pretty comfortable. One of the things I've learned by this is if the delta X and the delta Y, if it's too small, it'll run over the region because there's a certain delta X and delta Y that exist in the data sets themselves. You don't want to have it too tight, but you don't want to have it too loose either. So let's go through this now, and what we'll find is we'll find now the number of targets is 5. So we will just, let's say, let me find a convenient spot to stop and get. Here's where we'll go. We'll go to right here. We'll do a continue. It's busy working on the train, and then it'll work on the predict, and then it will give me a contour map that is a classification, not a probability. You can see the dots flowing across the screen right down here. Okay, now it's probably in, there we go. So what you see is a tighter classification. Let's take a real close look at this. What you see, let's first take off our background grid. And what you see is something you would like to see. What you're seeing is, first, you see these regions out in here is basically classified as a 5. All this region where it's sparse of data is all 5s, meaning even where points exist out here, saying that all this region, there's not enough data to support any classification that would come back from the predict. So this is all 5s. No data. There's no data in that 5 region. Now you start getting into, say, the 4 region right here. You'll see the region that is 4. All this data is 4, and even this is a little bit of 4. So it even says there's 3 data points here. I'm going to say that's a 4. Go down here to the 3. It looks like to me that the 3 is all in here. And then you get a 2, which it looks to me, there's 2 is just basically sitting in here. So here's a 2. And then you got the 1, which is this real dark blue. This is all 1. So you see the regions setting up. The 1, the 2, the 3, the 4s. And then the 5, which is out here, is no data. And that's the key of putting the background grid, is you clobber these regions out in here. And let's take a look and see what you find out. I'll put the data points back on, and then I'll go back to the non-edited version of this, shrink it way down. Now let's look at our contours, and I'll just let them come up here. Puts the targets there. Now you have a target 5. Let's just let all the contours come up at once, and we'll drag them over here. Okay, first let's grab target 1 and drag it onto our display screen, and here's what you see. Target 1, let's make it large. We're looking at figure 2. Okay, so these are contours of probability. What you find out is like what we were talking about before. You have this region. It's highly probable that, hang on, it's highly probable that you have data, 90%, 80%, that you have data of target 1 here and target 1 here. Highly improbable that you have data that's target 1 anywhere else. So you get the 0, it's existing all out in here. The existence of the background grid right here basically clobbered any false probabilities out here. Let's go ahead and drag in target 2. Here's target 2. Get rid of the background grid. Get rid of all the data, and then take a look at target 2. What you notice is you do have this little funny region right here that's sort of invaded into there, but that actually could have come from another source, and that source is the invasion of this target 3 into target 2's area. So you see a low probability pushing down. In other words, it's denser. You notice the blue is denser here. Dense. It is much denser population of that regime than the green. You'll notice that as the blue comes in, it's a little bit sparse up here, and the green is dense, so it has a higher probability of occurring right around in this area. So this is the contour of target 2, target 3. Very similar. Background grid's gone. What you find is that target 3, part of its regime was knocked away. So even though it exists all the way across here, part of the regime was knocked away by the existence of the red, or the target 1. Notice the target 1 coming across this blue area, the blue data has pushed the probability down. because in this particular area right here, right in here, you're sharing your space, your feature space. In other words, you've got this one and that one, this one and that one in this little area, so they're sharing space right here. Bringing target 4 in, you get a very similar concept. You have part of the red and part of the blue sharing this region right here. So you got this little hill, and you get a little hill over here. The blue and the red push the probability down here because there's existence of other data out in here. And finally, let's look at the background grid. This is the part I like the most. If you look at the background grid, you really see what you're doing here. You see that with the existence of the background grid, the probability, what you should have here is the probability that there is no data. In other words, the question for target 4, is there data? Is there, or basically, is there no data? No data. Well, it's a 90% chance if you're out in here that there's no data out here. So you may pick an arbitrary point of say 70%. Look at the 70% contour line. Anytime you get a target 5 of 70% or above, you say don't even believe the classification at all, because whatever it's going to tell you, it doesn't have. So essentially, this region out in here, there's no data from the original training set. Until you can get enough data out here, then the training set could actually lap over here, and you could believe the results you can get from here. But this is what you would call the belief zone, I guess. So this is what you should believe. If it's a low probability, you could believe that. So that's the whole reason we're doing this. And with that, the only other thing we have left, I don't even need to look at this anymore, so I'm going to clobber it. And then I'm going to go down and just run the last section, which does nothing but create the surfaces that are lit. Here, I'll even produce them all at once. This one I think is cool. Here is target 5. If you look at it, it is the probability. So where you see no colored data and the purple, very highly probable, there's no data. There's no green. There's none of the first 4. So essentially, that's it. You bring in the 4th. Let's see, the 3rd is where we had the, if you take a look at the 3rd here, you don't have that false hill or that ridge. Remember, in the 3rd point, or in the 3rd classification, you can look back, you see something very similar to this and very similar to this, but you also saw a hill sitting out here with no data around it, and then you saw a little ridge that was around like this. You notice that hill doesn't exist out here anymore because, first of all, it was false. There was no data out here. And now that you've seen this, you see that it only classifies that this region right here should be target 3. There is nothing out here. When you see this, if you had a feature that came in the future and it sat out right here, you know, the other one may predict that that was target 3. This one's going to say this is target 5, meaning highly probable this is target 5, highly probable there is no data right there to support any prediction you would get. And that concludes this. There's some other things you can do with this, and here let me let me do a couple of these things. Let's do something interesting. This is not part of what's required, but let's do something interesting to see some other things we can do with this. Now that we've set up our background grid, we can do something else as well. And this is not required of the project, but it's something that you might think about. Let's say we want to look at the original distribution of, say, feature 1. So here we're going to remove features 2, 3, and 4. We're going to just focus on 1. So I'm going to create a logic statement that says logic equals to, okay, since it's 2, 3, and 4, all I'm interested in is, say, if the target, with a plural, targets, and here I'm going to have to start using parentheses here. Targets, whoops, is, say, greater than 1. Oh, another. And I'm unsure whether I use 2 or 1, so I'm going to use 1. I'm going to go ahead and put a bracket there. Targets less than, say, 5. So this should take place. So then what I'm going to do, and I'm going to say features is equal to features up of, and what I want is logic what happened here. Okay, well, you know, before I do this, I think what I want to do, get down here and put a parentheses here, and I'm going to run this to that point. I'm going to save it, run it down to it. Okay, I want to do a step here. Whoops. Okay, so I want to look at logic. Okay, but I don't want, what I'm setting up to do is remove those, but in fact I want to do the reverse. Okay, let me do this again. Let's see what logic is. Now logic is first 1, so I'm going to keep those. Okay, now I'm going to do it this way because this helps me to figure out okay, I'm going to select this. I'm going to evaluate the selection, look at the features, severely reduce them, but I'm going to look at the feature. Wait, I'm going to do this to the targets then and look at the targets. Targets are dimension 1. This time I'm going to do evaluate the selection. I want to look at targets. I got 1. Let's look at the targets. Problem is I've got 2 targets. One is a 1. The next one is, or should be, a 5, right? Since I have that, the next thing I want to do is I want to say logic is equal to, and this time I want to say targets, targets equal to 5, and in the 5 what I want to do is say targets logic is equal to 2. Okay, so now if I've done this correct, let's save it and let's run it again. And I'm going to do a continue. I should have smaller values. Okay, the number of targets, I'm going to do a step. Number of targets is 2. I should be able to run this code now. So let's go ahead and run it down. The next thing, okay, so what you have in a feature space looks like this. Now there's only 2 targets, the background grid and one set of my data. The next thing is, let's do a continue. We'll run it down to here. Okay, so what you see is interesting. I'll have to do this to make the plot less busy. You see a background grid. So you see a envelope wrapping around data 1. Now, the non-existence of this other means, okay, if you did have the data, okay, then let's clarify what I'm doing. What I'm actually doing is I'm observing what the initial distribution would be of, say, feature or target 1 alone. I'm not using it to predict, but I'm just looking at this. Okay, it looks like I've produced this data looking like that. Now, there's no data. If there was a streak of data that came through like that, like we had earlier, it would reduce this probability down right around in here and maybe classify it differently. But I'm only looking at one data, one set, because I want to see if I can get the original distribution of one of these. Okay, so looking at this, let's see, continuing. Oh, I would throw the targets on there. Oops. So there's target 1, there's target 2. And now I would continue and end up with 2 probabilities. So here's my probability of target 2 and probability of target 1. If you look at it, let's put them both together in here. Go ahead and get that. What you notice is the probability of target 2, which is now the background grid, is fairly high. So high probability, in other words, the non-existence of data is all out in here. The existence of data looks like a little probability distribution that you might see, and that's in essence what I used to produce this. I used a Gaussian here. Well, here I'll show you. Well, I'll show you here. I used a Gaussian that had a principal axis going this way and one that had a principal axis going that way. I rotated around a certain angle, and I had a standard deviation in this direction, say SD x prime, standard deviation in the x prime, or say standard deviation x prime. Then I had a standard deviation y prime here that went out this way. So you can see it's tighter here than looser here. And this is the way I produced this data. And what's interesting is this last set, you really get to see, okay, here's target 2, but here's the cool thing, here's target 1. And if you rotate around, you'll see a distribution. Now, it doesn't look Gaussian, but let's take a look at this. Let's go back and change, for example, let's look at, first of all, let me take all my breakpoints off, and I'm going to go back, and my whole goal to run this next time is to get this plot 31 that we're looking at right here. So let's dock this away so that they're all together there except 31. And we're going to look at the effects of changing G. I'm going to drop G to 1, and I'm going to quit, and I'm going to rerun it. We'll have to be patient. It'll take a second. It produces all the plots, and then finally it produces my plot I'm interested in. Doesn't quite look like a Gauss yet. So let's even take C completely out. Let's take G completely out. Let them be our defaults. Run the code again. I'm going to do some stuff to make it look bad in a minute. Oh, I need to do a clear figure. Okay, so wait. I need to clear the figure. Oh, I can't clear that figure and then do that. Number of targets. Yeah, I can do that. Okay, so let's try this again. See, I haven't cleared these figures. Alright, so what you're getting on the figure 31 looks like that. That doesn't look quite right. It's not classified tight enough. It's just a bowl over the top of your data. So let's go back and say, let's go back and put in G is equal to 1. Okay, so here's our plot again. Still a bowl. Let's go back and play with this until we get, let's say I had 25. And let's run that. For that matter, I don't need the breakpoint at the very end. Okay, things are looking pretty good now. I'll go ahead and take that breakpoint off. What you see here now, it's starting to look more like a Gauss distribution. Although if you look down this axis, it doesn't look Gauss-like. But if you look down that axis, it does look sort of like a Gauss distribution. So you might want to play with this just to sort of see. Okay, I might put in C. Let's see what effect C has on it. This is what I mean by experimenting, so to speak. C doesn't have the effect that I'd like to have. It created dimples along the top. Still looks semi-Gauss along that axis. But we might want to drop this to like 15 and take the C back out of there. We're maybe making a little progress. Starting to collapse. I'd like to see these edges collapse up and be a little bit smoother like this. Along in here I look pretty good. It's telling me that looks an awful lot like a Gauss distribution. It should look like a Gauss distribution around in here. However, you know that it may have to do with the density of the background grid. I might actually be able to change it and fiddle around with this until I get a nice Gauss on both sides. So in any case, I'll leave the more fiddling up to you. I might do it some, but I think the point is made at this point that by just pulling out one feature and a background grid, you can look at the probability density of, say, just that feature without the other features there. I wouldn't use that as prediction. I would just use that as an educational thing to look at it and see what you might be able to infer from that. Depends on your data set, I guess. Okay, so that concludes this, and we're pretty much done.